Timer starts. Alrighty, thank you everybody for watching today's video. We are presenting today in parallel sorting algorithms for our parallel research project for the end of the semester. Alrighty, so why does sorting matter? Well, first of all, we see it all over industry with huge data sets that need to be sorted, whether it be integers, strings, or just data that is being collected. It's also a non-trivial problem that we see in our everyday world and in computer science in general. And then general purpose sorting functions, right? And whether it be in interview questions or again, in industry, a lot of problems require sortings, and it's applicable to multiple different algorithms that we see not only in our academic career, but in our work career as well. So to start off, we're going to start off with the simplest and one of the first algorithms taught in academia, which is bubble sort, because of the simplicity of it. And when you ask people to sort an array, usually they come up with some sort of variation to bubble sort. Now let's go off and start off with the state of the art when it comes to parallel algorithms for bubble sort. And the state of the art really, of course, since this algorithm is not being used in industry or to solve big problems because of its time complexity, a lot of the research papers are mainly for academic purposes. And what these academic papers show is the different ways one can parallelize an algorithm, such as bubble sort, whether it be in different architectures like a CPU versus a GPU architecture, and understanding the different runtimes between architectures. Now, the implementations that we took was two. The first one was the odd even sort, and the second one was the divide and conquer approach. So on to the odd even bubble sort parallel approach. So this sorting algorithm focuses on having two different phases, an odd phase and an even phase. And each phase is going to focus on comparing elements that are adjacent to each other. So for example, step number one will be executed by thread number one, and step number two will be executed by thread number two. Now, what the odd phase does is it compares those adjacent elements as stated before. So a number or an element in index 0 will be compared to element or on index 1. And then the next index that will be compared will be index number 2 compared to index number 3, and so on and so forth. So these threads will execute in parallel and sort the respective phases until the array is fully sorted. And now moving on to the divide and conquer approach. Now, when we hear divide and conquer, usually we think of recursive algorithms. So we decided to take an iterative approach. Now, in this example here, we have an array of size 20, where the maximum number is also 20. So for our approach, what we decided to do was split up the array into the amount of threads that we had. So in this instance, we have 4 different threads, and we split up the sublist. Now, the sublist, as you can see, the numbers are distributed in a unique way, in the sense where thread number 1 or sublist number 1 will take care of integers like 1 through 5, and then thread number 2 will be 6 through 10. As you can see, it's sorted in a way for the sublist where it's minimum to largest. And then in the end, these threads will sort the respective sublist, and at the end, the main thread will merge those lists all together by using some nice Java functions. Now, some of the challenges faced with bubble sort. With the odd even sort, it's actually a lower runtime than the sequential bubble sort version. And this is based on the overhead of creating, starting, and stopping threads. And then for the divide and conquer approach, manipulating the list before parallelizing the algorithm was sort of the tricky part, because the parallel algorithm itself is just regular bubble sort. The only thing that you're manipulating is the list and how you're splitting it up. Now, for the experimental resorts, as stated before, the odd even sort is a lot worse than the sequential sort, but the parallel divide and conquer with a total of 16 threads does end up being better than the sequential version when you have 10,000 more elements in the array.
Okay, and then the next sorting algorithm we're going to talk about is merge sort, which is another super common algorithm that's taught usually to first or second year computer science students. And our specific implementation So the problem with merge sort is that splitting up the arrays is a relatively simple task. But the challenge comes when you're trying to merge those smaller arrays back together. That's where the real complexity comes in. So even if each recursive call you made created a new thread, the bottleneck comes when you're trying to merge those arrays back together. So the algorithm that we ended up using in our approach has been described for a long time. It's back in CLRS, and then it's also, even in still modern research papers, this is the algorithm that a lot of cutting edge research is based off of. And the idea is that instead of going through each element in the row and trying to figure out, which element or which array to take your element from, you're going to take each element and then search in the opposite array and find where it would belong in that sorted array. And then based on that index of where it would belong, you can calculate in the merged array which index this element should go. And so then if you have n threads, if you have a thread for each element, you can do the merge in log n steps. So instead of the algorithm being n log n as merge sort normally is, this sort has a theoretical complexity of log squared n because you're doing log n to do the merge log n times.
Yeah, and then to kind of visually explain how this algorithm works here, we can see we've got like two sorted arrays, right? So this is, in merge sort, you already have two separate sorted arrays, and we're going to merge them into one single sorted array. So in this case, we have a couple different threads. Each thread is in charge of an element like we discussed earlier. And the job that each of these threads are doing in parallel is building this auxiliary array, right? And so each of them are modifying this auxiliary array simultaneously. So the blue thread and the red thread, and these are all, keep in mind, let's say this is 5 unique threads here. They're each doing this search. They don't really interfere with each other. And this blue thread, for example, will say, okay, where does 1 belong if it were to be in this other array? And it would say, well, index 0. It's also an index 0 in its own array. Therefore, it's an index 0 in the merged array. And so that's how we can get this idea of like building this auxiliary array all at once from numerous threads doing work on their singular element. And these are using binary search, right? So these are log n searches.
And then we ended up implementing this sort in both Java and in Rust. So for Java, the paper that we were basing our algorithm off of called for using a parallel for loop. And originally in our implementation, we tried just splitting up the array and giving each thread like an equal chunk of the array. And then we decided to switch it up and try doing a parallel int stream instead. And originally, when we just split up the array, the parallel version was much, much slower than the sequential version. And then when we switched to the parallel int stream implementation, it still is a little bit slower than the sequential sort, but it became a lot closer than it originally was. And we believe that this implementation would be faster if we just had more processors and more threads, because this algorithm is really meant for use on like server computers and things like that, where you have a very large number of threads and large number of elements to be sorting.
So this is actually a very interesting and difficult algorithm to implement in Rust. Rust is sort of uniquely suited, not for this algorithm, it's just like uniquely like not suited. Rust has this idea of a borrow checker, which ensures that it basically ensures mutual exclusion and prevents data races. So when we're trying to build this auxiliary array, all these threads are trying to access this shared resource at once, and that makes Rust extremely unhappy. So it will let you do this if you have like atomic integers, and it can guarantee that you're not going to get this weird concurrent access. But that's very bad in terms of like how long it takes, because then we have to convert to atomic, do our merging, and then convert back. So obviously that would be slower than if we had simply just done a sequential merge. However, I did want to kind of illustrate what this would look like if it were implemented, and show that it is faster. So you can use what's called unsafe in Rust. Rust will let you break a little bit of its rules sometimes if you use unsafe. And so I implemented an unsafe version of this where you have concurrent access to this, and you can do the concurrent modification of the vector. It is faster. If we go to the next slide here, we can see when we get to very large arrays like 10 million, 100 million, and we're getting past this this barrier of having to create the threads and do this little overhead, it becomes actually significantly faster. Unfortunately, this is only measuring the time it takes to do the merge itself. In this case, we still have to kind of convert to unsafe vectors and then convert back. So in practice, this is a bit slower. But this is kind of a proof of concept that the merging itself, actually creating this single sorted array from the two sorted arrays is faster in parallel in Rust.
Okay, so the next algorithm we're going to be looking at is insertion sort. Once again, we're commonly taught this in university. It's an order n squared sort. And in terms of the cutting edge, not many research papers delve into insertion sort because, again, it's quite slow as compared to quicksort or merge sort, where more researchers have looked into it. But one key idea for breaking and implementing sorting algorithms in a multi-threaded sense is to actually break arrays or whatever your structure you're using into chunks, sorting the individual chunks using different threads, and then performing some kind of merge operation. And in the Java implementation, we decided to do an n-way merge. So we can take a look right here. So of course, this is our input array. And the first task is to, again, split the array into different chunks, depending on how many threads you want to use. For this example, we're going to use 4 threads, so 4 chunks. The next step is to actually sort these individual arrays using insertion sort. So basically just sequential insertion sort on each of these arrays. And you can see our threads right here went ahead and sorted those individual arrays. And then after we join all the threads, make sure all of their work is completed, we can actually merge all of that using an n-way merge. So this basically one thread, perhaps the main thread, is performing this work, basically has a pointer at each of the subarrays and eventually merges them back into a sorted array, fully sorted array. So here we can take a look at some test cases just using integers. This implementation can work with generics, so basically anything implementing comparable will work. And you can see even for arrays that are 1,000, which is fairly small for how big arrays can get, already a parallel version of insertion sort with 16 threads is faster, and same goes for higher array sizes. We also decided to create a custom Java class called slow comparing integer. It's basically just a class with an integer, and in the compare to method, we put a thread.sleep, so it takes longer. We were just curious how the insertion sort would work when faced with objects that take a while to compare. And you can see even for array of size 10, the overhead of all the threads is still comparable to the sequential version, which is pretty crazy. And then if you go up to even 100, an array of length 100, it's significantly faster. And we didn't even test for array lengths more than that because it just took way too long. So that's it.
All right, now I'm going to talk about insertion sort in Rust. So I actually went and, based on the research I did, implemented a slightly different method for doing insertion sort. So we're still doing fundamentally an insertion sort, but the merging technique we use is a little bit different. And the library that I actually used is something called Rayon. And so this is really a state-of-the-art library that you can use with Rust to implement data parallelism. If you're ever using Rust and have the opportunity, like you need to parallelize something, highly, highly recommend you check it out. It's written by a core contributor for Rust, and it really makes it nicer. It makes it a lot easier to write things in a safe way where you're not going to end up with any race conditions or those sorts of problems that you would get from just like starting up threads and then trying to do thread.join, that sort of thing. One thing you do have to kind of subscribe to is some functional programming ideas. So if you're familiar with map and reduce, those concepts are something that's very native to Rayon and how it ends up actually working. And so that's kind of, I would say, a prerequisite for being able to use the library, but super approachable, even if you're not familiar with that kind of stuff, and highly, highly recommend you check it out if you are trying to use Rust. So something else I kind of looked into is there's this C++ 11 sort. This is really a state-of-the-art algorithm. And even though it's actually a quick sort, so you can see we're starting basically a bunch of quick sort slabs in different partitions. And once we get to a small enough array, we're going to just do sequential because it doesn't make sense to spawn 16 threads to sort of 16 length array, something like that. Then so you basically sort each of those in parallel, and then you're going to do merges, a bunch of little merges of all those arrays coming back together. And that lets you, versus the n-way merge, which is kind of the approach that Adam ended up taking. The advantage of this is that even though you have to do more merges overall, you can do more of those in parallel. So you're not bottlenecked by the main thread has to merge. Say you have 2,000 partitions, doing a 2,000-way merge is going to be very computationally expensive. So if you do a bunch of little two-way merges, that can help you split up the work over more threads more effectively. So kind of just taking a look at how this actually works. Here we have a big array, right, going from 1 to 20. Those are the different things we have. And all I've done is kind of chop the array in half. So just to keep it simple, I'm only using 2 threads here, but you can easily scale this to have many, many more threads. So we've got the blue thread and the red thread. And what's going on is within each of those threads is going to kind of chop up its own work into pieces. So in this case, we've decided to have like 8 partitions overall. You can scale this. This is all something you'd want to tune to figure out exactly for your comparison and how many threads in your machine and cache and all that stuff, how exactly it's going to work best in your machine. But this is just sort of an example of what it might look like. You've got this, and each thread is going to kind of do one chunk of this work at a time. The interesting thing about this is that the threads are queuing this work up, and these queues are made public to other threads. So blue is working on this array, this subarray that has 4, 7, and 9, right? And then red is working on the partition with 18, 17, and 6. And then the plan is for blue to do 1 and 3, and to do 2, 8, and 10, 19, 20, and to red to do all the ones that are in its queue here. But that might not necessarily happen, right? Because different arrays, like if you look, it just so happens in this example, completely by accident, we've got the blue threads, all the blue threads partitions are already sorted. So depending on how exactly you implement your insertion sort, this is probably going to occur a lot more quickly than the red thread's going to get through its sorts. And this is going to happen in practice as well. Sections of your data are going to be already sorted, or sections are going to be quicker to sort than other sections for whatever reason, maybe scheduling with your threads, all kinds of things can happen. And so the question is, how do we continue to parallelize this if blue like blows through all of its tasks? So we can look at an example of how this actually works within Rayon, and you can implement this in other languages, but Rayon just makes it really easy to do. And basically it uses a technique called work stealing. And work stealing dates back to multi-Lisp, which is an implementation of Lisp that's kind of designed for multi-threaded programming. And the idea is that if something like this happens, right? So blue has blown through all of its arrays, all the little partitions, sorted each one of those individually. So we're looking, blue's like, okay, I've got nothing to do. Meanwhile, red actually has to do sorting, so red's going a little bit slower. So what can happen is blue can just do some, commit some petty theft here and just go say, you know what, red, I'm gonna steal the rest of your work because you're just going too slow and I'm sitting around here doing nothing. I gotta have something to do. So I'm just gonna go over and steal this array with 11, 12, and 5, as well as the rest of the work in that queue. And the way that actually this ends up happening is basically a bit's getting set inside your data structure here. And so you're setting that bit so red knows, okay, someone else has already stolen this task from me. Don't start it when I finish. And so let's say blue is now trying to sort this array, and red, or it could be another thread. Remember, I'm just using 2 threads to kind of keep it simple. But if you have, 8 or 16 threads, you can see how some are going to finish earlier. And this can really help it can help a thread that maybe got swamped with a bunch of really difficult to sort arrays from being the bottleneck for everybody, because everyone else can come in and steal once they're done. And so red can actually come back and say, okay, now that I finished my thing, I'm going to steal this back. And then basically it ensures maximum throughput. Everyone is going to be working on their thing, but you also get really good cache performance out of this, because all of these, like all the contiguous stuff, so like the 4, 7, 9, 1, 3, that's all contiguous in memory. And most likely it's going to be mostly accessed by blue. So you don't get as many memory bottleneck issues. It has very nice cache qualities as well, which makes it really good for, state-of-the-art performance. So, okay, after we get this done, right, we have a bunch of these sorted partitions. We have all this done. If we don't want to do an n-way merge, there's nothing wrong with an n-way merge per se, but if you have a huge number of partitions and you're just doing using one thread to do an n-way merge, you may not get the best performance. The more partitions you have, the slower that's going to get. And so what you can do is you could basically use the .reduce function. And what this is going to let you do is take smaller subarrays and merge those together. So here's one possible execution you might get. You might get a very binary tree kind of look to this, where you're merging 2 adjacent arrays together, merging 2 adjacent arrays together, merging those together. Eventually you get back to the big completely sorted array. you can also look at this from the standpoint of each individual. Like if we look at this next example here, it doesn't have to happen in that order. So the ordering is something that's kind of determined based on what's finished first and where the threads are available. And so like in this case, you can see that we merged those first two partitions together. And then we decided for whatever reason that we wanted to merge the 2, 8, and 10 in before 19 and 20. And a reason that this might happen is this merging can actually start to happen in parallel with the sorting that's happening from before. So say 19 and 20 was taking a really long time to sort for some reason. Then instead of 2, 8, 10 waiting for it to be done to do the reduction, we can just immediately start merging that in with maybe this other work that's already done. And so it gives you you have basically the lowest chance of any particular slow operation slowing down the entire business. Regardless, you're going to have to do basically the same number of merges eventually to get to your final state. But ideally, you're going to get something kind of like our last slide, right, where you can have 4 threads working here, and then 2 threads, and then 1 thread, and you kind of limit. You only have to ever do a 2-way merge. And so the performance for this is pretty staggering. It's fairly highly effective based on the results that we did. For very small arrays, all the overhead is obviously not great, but as soon as you get up to 100,000 or 10 million, which is when you would actually start caring about performance, right? No one is going to be like, it took an extra 0.6 milliseconds to sort my array of size 10. This is such a disaster. When you're really going to start caring about performance, splitting things up in this way and kind of getting this, you get merge-like performance because of how big the array is. So overall, we still got a lot of work to do, but our early results are very promising for some of our sorts. What we want to kind of focus on for each individual sort. For our merge sorts, we want to try to convert those to get better performance, because we are, especially with the Rust version, we're having issues with performance and getting that to work. And we definitely want to at least try to get the Java version consistently faster than sequential performance. Then for the insertion sorts, I want to continue exploring cache and seeing if there's, in some papers I've read that memory bottlenecks start to make an issue. Like if your array gets big enough that it doesn't fit in cache, then you can start getting really substantial slowdowns. So I want to kind of do a comparison and see what you can do about that, how you can kind of minimize memory usage, optimize that sort of thing, as well as just kind of tuning the parameters, like how many partitions is best. Do we want, if we have 16 threads, we want 16 partitions? Do we want 128? Do we want 32? What's the right number there? And then for our bubble sort, we also want to pursue trying to make that actually faster than the single threaded approach. I think some of the limitations on some of these, especially like the merge sort of are born out of the fact that the machine that we have access to with the most threads is just 16 threads. And some of these merge sort algorithms are really designed to be run with n threads and more of like maybe a GPU kind of context. And then bubble sort is just, it's bubble sort. It's don't use it. It's interesting theoretically, but not that we recommend to use it. So with that being said, we'll take questions if anyone has any, and thank you for watching. I guess we can't take questions, right? Because this is the video.
Don't worry about it. They can put it in the comments. That's totally fine.
They can put it in the comments. Yeah.